Okay, so now we're starting our seventh meeting in M269, and today we'll be talking about the searching algorithm. In this subject, actually, we will go through different types of algorithms. And by the way, this class or this lecture will be divided into two parts. Today we'll try to finish half of the part, and then in our next meeting this week we will continue with the second part. So searching. Searching means how to locate a particular item from among a mass of other items. So you have a pool of items, you have a container which include huge number of items, or it might be small number of items, and then how to locate a particular item among these other items. And now in our days, in current days, we are actually using search in every single hour in our life. Everybody is searching. You search using your own mobile, you search using Google, you search using your computer or tablet to look for your operating system, your files stored in operating system. So we are searching and applying searching everywhere. So why it's important? Because it's actually affecting our life, our daily life. Do you think if Google is slow in searching, do you think that it will be the most popular search engine nowadays? Definitely no. Yes. The reason is that users or the customers or the end users are always looking for high performance systems. So that's why
Let's
it is
start
very
first.
important to have or develop and enhance the performance of searching algorithms. Now we have already talked about different structures, including the sorting algorithms, and actually some of the concepts that we have covered in sorting algorithms are similar to what we are going to cover here, especially when we talk about the binary search and the quick select. Now, in this lecture, we will talk about the binary search algorithms and the quick select. And in later lectures, we will talk about the KMB algorithm and also other structures. So let's start first. So here was going what we are going to cover: the hash, the linear, binary, quick select, and hash table and hashing. And in the second part we talk about the KMB and also the search tree, which is binary, and the AVL trees. Now, what do you mean by linear search? Linear search is actually a very simple process of searching where we need to examine every single item we are searching in. So for example, if you have the list, what you can see in the slide, which include these 10 items, and these are the values stored in the list, and let's say we are searching for the value 33. What you need to do in the linear search is to compare every single item with the with the keyword that we are looking for. So 33 will be matched or compared with 10. If not, then move next. 14 with 33, no, then next, and so on until you reach your target. So in this case, we need to go through O of n operation, because the best case is right is to find, in the best case, to find the first item as the key item, the one that we are looking for, and then you will get it in O of 1. But we don't consider the best case. What we consider is the worst case. So the worst case is when the 33 is at the end of the list, which means you need to go 10 times till you reach the item you are looking for. And this is actually the for loop, and then check whether the item equal the value for every single item in list. Now in binary search, complexity gets better, where we managed to reduce the complexity from O of n to O log n. As you know, in the serial, or linear search, we need to go through every single item in the list, and that's why if you have n item, it needs from you log n. Sorry, it needs from you. Let me erase it. Okay, if we have n items, then the process of searching has to go through n possible items as the worst case. But in case of the binary search, the process is different. In binary search, we have a tree, and we have left and right child. So in this case, what you need is to search in one type or one part of the tree. You are not going through both parts of the tree. That's why we said if you have only one or half paths, then you just need log n as a complexity. Now, how does the binary search work? For the binary search, in order for the binary search to work, it must be sorted. So if your array is not sorted, then your binary search will not work at all. So the first step is to sort your list, and we don't care whether you sort it ascendingly or descendingly. So let's say you have this kind of lists where it is actually sorted. Minimum is 10 and maximum is 44. The first step is to find the middle of the list. The middle is actually the values between 4 and 5. So this is the middle. 4 and 5 is the middle. So 4 plus 5 is 6. Sorry, 4 plus 5 is 9. 9 divided by 2 is 4.5. So 4.5 will be 4 actually. We can consider 4 as the mid of the array. Now, what we do is to compare. So for example, let's say what we have or what we are looking here is for the number 33. So you compare your 33 with the middle. If the middle is bigger than 3, then you search to the right side. If it is smaller, then search for the left side. So here 33 is bigger than 27. So what we need is to search only half of the array. So we are saving the time in searching in this part of the list. Now, after that, since I reached to the 31, let me back again. See, I'm searching for the value 33. I found that 27 is smaller than 33. So I will ignore the 27 and all the previous part. Now I will start from 31 and till 44. So the next step is, now this is a new new value 31. I need to find the mid of 31. The mid of 31 is 5 plus 9. No. 5 plus 9. 14, right? 14 divided by 2. 7. So the new mid is here. This is the new mid. Now I have minimum, high, and this is the mid. Now compare 33. Is the 33 is this is the 33. Is 33 smaller or bigger than 35? The mid. It is actually smaller. So I need to search the other side. So I'm going to take out this part, including the 35. Now what I have is only two values, 3167. Now what is the middle between 5 and 6? 5 plus 6 is 11. 11 divided by 2, 5.5. So 5.5 is closer to 5. So the new mid will be 31. If you are not, we go because, no, we went to the left because 33 is smaller than 35. We go, actually it depends on the mid. The mid is 35. We are looking for 33. And we said that the list is sorted. So definitely 33 is before 35. That's why we go to the left. You got it, Sonia? No. 27 is smaller than 33. No. See, guys. Let's back again here. Here the mid was 27. Now we are looking for 33. So 33 is bigger than 27. That's why we go to the right side. In the next slide, we reach where the mid is 35 and the target value is 33. In this example, by the way, the target value is 31, but I started the example by saying 33. So let's say 31. So 31 is less than 35. So we have to search on the left side of the list. Now we reach to this point. The mid is 6 plus 5 divided by 2, which is 5. So the new item, the new mid is 31. Then 31 equal the target. We stop. So we return back the value at position 5 or location 5. Okay, great. This is the pseudocode of the binary search algorithm. You see how we're checking here. This is the condition, the if condition for specifying whether the value is below or above or equal the midpoint. And every time actually we set new midpoint. Here you can see the code. Okay, yes, Lama. Where exactly? Where? Which line? Okay, if the midpoint is less than x. No, for every single condition has its own يعني its own status. If the value of x, okay, we are now comparing with x, the value that we are searching for. If x is greater than the midpoint, then we have to change the lower bound. The lower bound has to be changed from the mid plus 1, so it go to the right. See, exactly, here is the point, here is one point, here is another point, and here is the mid. It's saying that if the value is greater than the midpoint, then this is the midpoint has to be shifted to the right, one side. But this is the meaning of lower bound. So this is the lower bound equal midpoint. So the lower bound will move from here to here. Yes, exactly. Okay. Now moving to the other type of algorithm, which is the quick select algorithm. Quick select algorithm, it's actually the same structure as the quick sort algorithm, which I think all of you like this algorithm. This is actually, even you can see from the name, quick list, quick select, afwan. Quick select is actually part of the quick algorithm. It has the same structure. It do sorting based on quick sort, and the only difference is the partition now, which is going to help us to search for a particular entry. Now the complexity of this algorithm is O of n, and let us see how the algorithm work. Actually, I'm not going through all the steps since we have already covered the quick sort. So starting the concept is as follows. If let's say you have this structure of elements, as you can see, first is to find a random element x from this given list. It's randomized, okay, and the selection of the pivot value should be random. So let's pick up a random pivot value, we call it x, and partition the whole element into 3 sub-elements. So this is now one list. First step, choose one of these elements as pivot value. Let's say we choose this. Now this is called x. What you do now is create 3 sublists, or make a partition. Partition the list as into 3 sublists. Now these sublists are called L, E, G. The E will include all the elements from S which has the same value of x. The group G, or the partition G, must include all the items that have values greater than x. And L has the set of elements with values less than E. So E has the same value of x's, the selected pivot value. On the right side, group G has values more than x, and on the left side, group L has values less than or smaller than E. Now if you want to search, actually it depends, or the situation will be much easier because it will help you to decide whether you go to the right or go to the left based on the pivot value that you are selecting. Here is the partition of S into 3 different subgroups, and it takes O of n. You see now, here is the if statement. If we compare, if is greater than y, then we add it to L. If it is equal x, then we add it to the group in the middle E. If the value is bigger than the pivot value x, then we add it to the G list on the right side. And by this, we are actually filling up these three partitions from the main input list, which is S. So S will be generated, or will generate three different lists. We have the L, E, and G. You got it? And this is how the quick select algorithm actually in Python work. This is the Python code. Now, in terms of hashing and hash table, the hash table is a data structure where actually we are storing the data with some association. So in the hash table, we don't care about the format of the list, what data type, but we care about how you index these values. For example, now let's say we have some student in this list. We have, for example, Abir. We have Ahmed. We have, who is Sausan, and let's say we have Lama. Now, I'm not going to search by name. I'm going to search by index. So the hash table will be built somehow like this. Lama will have the value 5, Abir 4, Ahmed 1, Sausan 7. So when I search, I will search by index instead of searching by the entry itself. And this is actually going to enhance the performance and the efficiency and the complexity of the given algorithm. Now we're going in details and more details on how the hash table works. Now let's say you have a list, and this is called the hash table. It's just a list. This list or this hash table has 11 locations from 0 to 10, as you can see. So the length is 11. Now what we need is to map some entries to some locations. Sorry. One way of mapping, to perform mapping as a hash function, this is an example, but in reality, because this is actually widely used in security. So we have different hash function like SHA-1 and MD5 and MD4 and so many other hash functions. But one simple idea is to use the modular operation. Modular operation. So let's say you have this list of numbers 54, 26, 93, 17, 77 and 31, and we need to store them somehow in this given hash table or list. So one way is to do the modular operation. Since we have 11 items in the list, the maximum number of items we can store is 11, then you should not allow any function to generate a value that is greater than 11. In our case, it must be 10 maximum. So what we do in our hash function is to take the input value and then modular 11 and store it in that location. So 54 modular 11 is 10. So we will put 54 here. This is where we store the 54. 26 modular 11 is 4. So 26 is here. 39 modular 11 is 5. So here is 39, and so on until we reach this hash table, which actually have stored all these numbers in it. Yeah, only the remainder. Yes, we apply the remainder, which is the modular, and the result will indicate the location or the position of the entry in the hash table. Now in this diagram we have actually 6 slots from the hash table because we have 6 elements. So 6 out of 11 are occupied, and that is actually called or referred to as the load factor, and it is referred to it by this symbol, which is the lambda. So lambda equal 6 over 11 means 6 entries are occupying their location in a hash table of size 11. So the empty available spaces equal 5. Now, what question may arise in your mind while we are doing this? Yes, that is the question, exactly. What if two numbers generate the same or have the same remainder? Are we going to override one of them? Actually, there are so many solutions for this. No, there is so many solutions. But if two items have the same remainder, then we call it in the field or the science of hash, we call it collision. So there is a collision, يعني تصادم. So the best hash function is the one that can minimize the number of collisions. We cannot reach to a point where we have no collisions at all, but we can minimize it as much as we can, as much as possible. So a collision happens when two items are sharing the same location in the hash table or the same index in the hash table. This is called collision. And now we will see how we can deal with such problems. And of course, for the complexity for the hash function is O of n in the worst case, and the best case is to find it directly, and it takes O of 1. Because actually finding the element in the hash, it takes O of 1. But to reach that item in a list of n item or n indices, it takes O of n. And that is the worst case. Now, the problem of collision, to solve this problem, we call it resolution. Resolution is how to solve the collision problem. One way to do this is the linear probing, or call it open addressing, and the second is chaining. For open addressing, actually all the elements stored in the hash table, and if there is a collision happen, then we need to go and search for the first empty or free slot in the table. For example, let's say I have this table and we have these slots in the table, and let's say I have here 5, 3, 7, and then I wanted to store a value 8, which by some calculation it must be stored here in the same location where we have the 7. This kind of resolution or solution said, instead of storing it in 7, go and search from 7 downward into the first location to store the 7. to the new item. So the new item will be 8 here. That is the next available slot. This is called linear propping. See, for example, here, the array, after applying the modular operation, the remainder, the first element, for example, 1 must be stored in 1, second in 2, 42 in 2. But we did not store it in 2 because we already have this element stored in 2. So based on the linear propping, we move it to 3 because the 3 is available. So here is the actual indices after linear propping. Clear? Okay. Now one problem might occur if, let's say, now I already stored these elements 77, 44, 55, 20, 26, 93 and so on. Now I'm searching for the element 93. 93 in 93 supposed to be stored here. For example, this is for instance. So I'm searching for 93, and when I put the remainder, it directs me to number 3. But the content here, it's not 93, it's 20. Means there was a collision, and then it was fixed by the linear propping. So what should you do in this case? In this case, if you did not find 93 in its location, then you must start searching from this point downward until you find your keyword. So if there is collision, means there is more time for searching. That's why the algorithm that generates less number of collisions and can minimize the number of collisions to the minimum, then it can be more efficient. But for the chaining as a resolution, the chaining, it's very interesting idea where you don't store the item in the location here, but every single location in the list represent the head of a linked list. So when you have the, for example, 77 modular 11 is 1. So 177 is the entry in the linked list. 44 modular 11 is 1. So 44 is the second element in the linked list, and so on. So here we don't have actual values. Yes, it's not 0, it's null. So we don't have exact values, but it is a pointer or a head to the linked list. This is called chaining. Why is called chaining? Because we are creating chain of items. So the performance of the hash functions is actually different from structure to another structure. The best case is to find your item from the first hit. Then it's going to take from you O of 1. And that is a constant time for the search. But since we have collisions in many of the hash functions, so we need to apply some other linear search. So even if you go to the linear propping, you need to go for a search from the first index downward, and if you go to the linked list, which is the chaining, you still need to go search through the whole element in the linked list. So searching is there due to the uh, collisions. So we cannot come up with an ideal performance or complexity for a given function or hash function unless you examine what kind of structure they are using, what kind of resolution they are applying, and that's actually affecting the performance, overall performance of the hash function. Yes, of course. In the chaining lemma, when you reach the index, for example, the remainder was 9. So if 9, then you start searching from element here, from the first element in the linked list downward. So we are searching the first element of the linked list. Okay. So do you have any other questions? As this is the last function that we are covering today in the first part of the searching algorithm. Okay, great. Thank you for your contribution today as well.